we're going to cover many topics in this course during the quarter, and our first topic is going to be to give you some background, to bring you back into thinking about arrow pushing. For some of you, it's been quite a while since you took organic chemistry. I don't think any of you covered arrow pushing mechanisms at the level that I would hope, but that's what this class is really about, is to help you to understand which reactions are fast, which reactions are slow. If you see any organic transformation, can you understand at the level of breaking bonds and forming bonds? Now, I have some texts that I've recommended on the course Canvas website. 2 of them are available online. You just have to be on the UCI campus, and you'll have access to these textbooks because they are through the UCI library. There's a link. But the third textbook that I recommend is your sophomore organic chemistry textbook. So I think many of you will have taken organic chemistry here using the Gorzinski-Smith textbook, and I would hope you would have access to that still. Use a textbook that you're familiar with so you can go back and look up the mechanism for hydroboration, oxidation, or electrophilic aromatic substitution with nitric acid, things like that. But I've put answer solutions for the relevant chapters in the Gorzinski-Smith organic chemistry textbook, so you can look up the answers. And I'm going to ask you to work arrow pushing mechanisms out of there, and you can look in the solutions that I provided to see if your arrow pushing mechanisms seem plausible. Sometimes I'll have some suggested reading. You don't necessarily have to read these. It might be an interesting thing for you to look at. I would hope in this class that every once in a while you'll peer into some of the original research literature. I'm going to be giving you references to original research papers. And as you move higher in your classes from sophomore organic chemistry, you'll start to see more and more that people give you research literature to look at. And why would you want to look at that? You won't understand most of what you're seeing in those research papers, but the introduction to those papers is kind of this condensed, here's what the paper was about. And here's the gap in knowledge that this paper filled. So there's an interesting paper called The Iconic Curly Arrow that talks about the origins of arrow pushing that may give you some insight. We just passed the 100-year anniversary for the introduction of arrow pushing as a way to explain organic reactions, organic reaction mechanisms. All right, let me come back to this. I asked you to write out some sort of a mechanism. How many steps are there in this transformation? How many steps did any of you come up with if you count them up? 3 steps? 8? 2? Wait, what's going on? Is it 3 or is it 8 or is it 2? I mean, this is the problem. I mean, this is why we have a class like this. It's not always obvious. Does that mean some people are right and some people are wrong? You know, I ask you in this class, I will ask you questions on my problem sets, on my exams, to write plausible arrow pushing mechanisms. Sometimes there are 2 plausible mechanisms. One is short, one is long, and they are both plausible, right? But in this case, there's one that is more plausible than the others. And so these are common questions that we have. Why can't organic chemists agree on arrow pushing mechanisms? You know, even for simple reactions, simple transformations like this substitution that I'm showing you. I'm showing you a simple substitution of a hydroxy group here for an amino group. How hard can that be? Or maybe you might draw out some fancy arrow pushing mechanism and then you go look at the solution in the solutions manual and it's different. And your first question is, what's wrong with my mechanism? I wrote out my mechanism with knowing everything, I applied everything that you taught me, and how come my mechanism doesn't match? Everybody goes through exactly that, and this is common. So, you know, and then when you look in research articles, you might ask, how come my mechanism doesn't match what's in the research article? I'm sure the research article is correct, and does that mean your mechanism is wrong if it doesn't match what's... And the answer is no. These are all confusing questions that we have to address. Here's the real reason why you see this much disjointed and disagreement between people when they write out arrow pushing mechanisms for the reactions. And that is that organic chemists never really stopped to agree on what an arrow pushing mechanism was. Arrow pushing was first introduced about 100 years ago, about a century ago, but they never said exactly how it had to be used. They just said, here's this powerful tool for understanding resonance, for understanding how bonds form and bonds break, but they didn't say, here's the rules you have to follow. So we're going to fix that situation because we're going to start off in this class by all agreeing on what arrow pushing is going to mean. So when I ask you for a plausible arrow pushing mechanism, we all agree what you're supposed to be giving me. And the agreement is basically, I'm the one grading the class, so I make the rules and decide how it's going to be used. But what you will find is that I follow rules that are followed by the best organic chemists who are doing research on the planet Earth. The best chemists will follow these rules. And if you look at research papers that might follow a different set of rules, they're not following the same set of rules. So what is an arrow pushing mechanism? This is what I'm going to be asking you over and over again. I will ask you over and over, suggest a plausible arrow pushing mechanism for the following transformation. And when I ask you for a plausible arrow pushing mechanism, I'm asking you for a series in sequence of arrow pushing steps. And they are all going to be elementary reaction steps. What is an elementary reaction step? When you add those curly arrows and you draw the reaction or going to the next set of intermediates, an elementary reaction step has a single transition state. That means it is provable. That means we can do complex ab initio calculations to show that that step does indeed have one transition state. You can't do those, but you'll be able to come up with the right answers without doing complex ab initio calculations. But if we ever had to, we could resolve whether it really involves just one transition state versus a two-step process. And then the last thing, after we break it into a sequence of steps, like here's a step, here's a step, here's a step, 4, 5, 6, 7, 8, 9 steps in this mechanism. And each one of those will have a single transition state. In order to complete this, we then add the curly arrows. Right? So first is to break it down into elementary reaction steps, and then you can add the curved arrows as you're going. That's usually what most people do. So this is not a trivial mechanism. I put it up because I thought it might be complex. I put it up because I thought the substitution might fool you into thinking it's an SN2 type process, which it is not. And so this is what we're going to talk about. How can you look at a transformation and make good guesses about how to push the arrows and how to break transformations down into elementary reaction steps? Doesn't matter whether it's an interaction of a drug that's covalently modifying some RAF protein in a cancer cell, or some complex organometallic reaction that's going on in a reaction flask. I'd like you to be able to understand chemistry at the level of atoms and bonds and curved arrows. Okay, now we gotta agree on what these curved arrows mean. Because if we can't agree on what these curved arrows mean, then we're gonna be in trouble. And I'm going to scare the living daylights out of you by showing you this equation that I'm going to refer back to in a disguised form, but you won't actually be using this. And what I'll point out is that this is an equation that's very similar to something you've seen before. Back when you took freshman chemistry, it was taught by physical chemists who just cared about helium gases sticking together, or let's compress methane and raise the temperature and figure out what's going on. And physical chemists tend to be more interested in non-covalent interactions, not reactions that form carbon-carbon bonds. That's us. And so you learned about the effects of charge and something called the Lennard-Jones potential. Remember that? There was this mysterious 612 potential where you get closer and closer and something depends as the distance to the 6th power plus or minus some distance to the 12th power. And that's what this equation is right here. This equation right here is basically charge and the Lennard-Jones potential. There's a distance dependence to all of these. You can't really see the distance dependence here. It's hidden in this overlap coefficient. But what I'm telling you is that anytime you want to compare two transition states and figure out which arrow pushing is fast and which is slow, that's what you care about. Is this arrow pushing better or is this arrow pushing worse? When you want to compare two transition states, two conformations, two isomer energies, anytime you want to compare two of anything, you would think about these three effects. You would think about charge. Now I hope everybody in here has an intuitive understanding of Coulomb's law. It's like plus minus charges attract and like charges repel. And the closer you are, the more powerful those effects are. So I hope you understand this Coulombic term in there. And like plus minus is good and like charges repel. I shouldn't have to have a separate class for that. I hope you understand repulsive interactions. When two methyl groups bang into each other, they repel each other, right? If I hit my fist on the table, it doesn't go through the table because there's a repulsion there. And so I shouldn't have to explain that. That should be natural to you that when things get crowded, they become uncomfortable. So we don't need a separate class or some formal training to think about repulsion or charge, I don't think. But what we do need is a class that teaches us about this very mysterious looking term in this mathematical equation. Like, God, look how complex that is. You're summing over something, you're summing over all the atoms in one molecule and all the atoms in the other molecule. There's some sort of a coefficient thing here. There's some sort of an overlap term of electron density. And then there's the energies of something. Who knows what that is? And you know, all of these we think about when you draw two molecules coming close to each other. We do think about Coulombic effects. If you're trying to think about why it might be good for, you know, some sort of a lone pair to do a substitution, but that's problematic. There's crowding in there, right? And you'd see that crowding in the form of sterics. It's hard to do SN2 reactions at tertiary centers. But there's this last thing that is not sterics and it is not charge. It's bond formation. And that bond formation is captured in this term. And that's what we care about in this class. We care about forming bonds. Which arrow pushing to form bonds and break bonds is the best? So this is what we are going to use arrow pushing to represent. We are going to agree that charge is obvious. We don't need arrow pushing to represent charge. We're going to agree that sterics is obvious, and we're not going to use arrow pushing to represent sterics. We're going to use arrow pushing in this class. Every single curved arrow you draw is meant to represent things that we can't see and that we don't draw, and that's molecular orbitals. So to help you figure out which curved arrows are good and which ones are bad, we're going to think about molecular orbitals in this class more than you would have thought about when you took a sophomore organic chemistry course. So this is what everything I say about curved arrows in this class is going to be related to this complex mathematical equation, which I'll keep making this simpler and simpler until we forget about it. You shouldn't be spending your time in this class drawing out mathematical equations, or else you've missed the point of the power of arrow pushing. All right. Now, why do I feel confident in making a whole set of rules that I expect you to follow? I'm not actually making up these rules, and I'm not the one who decided that those curved arrows should represent these molecular orbital interactions. There was a book by Ian Fleming. There's another Ian Fleming that wrote the James Bond movie series, but this is a different Ian Fleming, a silicon chemist. And he wrote a famous book that me and all my colleagues learned from when we were students. It's maybe at your level or a little more advanced. And he makes this seismic comment in his book. He says, curly arrows, when used with a molecular orbital description of bonding, work as well as they do, simply because they illustrate the electron distribution in the frontier orbital. And for reaction kinetics, it's the frontier orbital that is most important. So what Fleming was saying was, if you care about which reactions are fast and which reactions are slow, if that's what you'd like to determine, then you should use curly arrows for that, right? So that's why we do this. It's because he kind of set up the central canon of mechanistic arrow pushing. In this class, we are going to use curved arrows to depict the interaction of filled orbitals with unfilled orbitals. That's what we're doing when we draw the curved arrows. So when you draw a curved arrow that looks like this with ammonia doing an SN2 reaction on methyl bromide, what you're really saying is that the non-bonding orbital on ammonia is interacting with the anti-bonding sigma star orbital for the carbon-bromine bond. That's what those curved arrows mean. Now we're just going to draw the curved arrows, but if you ever have to go deeper, we've got some powerful tools to go deeper than that. But most of what you should be doing is just drawing curved arrows in this class, but develop an intuition for what that means. So I'm going to give you some rules just to remind you, go a little into more detail on how to use curved arrows that is powerful and consistent with this basic canon of mechanistic arrow pushing. And let's go ahead and talk about those rules for arrow pushing. I'm going to give you 7 rules for arrow pushing on every assignment that you turn in. On every exam question where I ask for a curved arrow mechanism, I expect you to follow these 7 rules. And you may have been following these the whole time that you took sophomore organic chemistry. Some of you will have been following these already, whether you knew it or not. Might have been intuitive to you, but I need to state these rules explicitly and give you an understanding for why we've created these rules. So, rule number 1 is we're going to draw correct Lewis structures. That seems pretty simple. I seem to remember I don't remember when I learned to draw Lewis structures. Maybe it was general chemistry or something, but we're just going to agree to draw correct Lewis structures. Rule number 2 is arrows are going to start with bonds or lone pairs. Every arrow you draw is going to either start with a bond or a lone pair. Every arrow you draw is going to end on either an atom, preferentially, and then in some cases on bonds. I'll allow that. I'm going to introduce something called the 3-arrow rule. Enough said. I think you'll grasp that pretty quickly. I'm going to tell you not to have any steps, any arrow pushing steps that are termolecular, and I'll explain that term. I'm going to introduce some symbols for you for proton transfer steps, symbolic acids and bases, so that we don't overstate what we think we know. And then I'm finally going to tell you that make sure H is always attached to something. Those are our rules we're going to follow. Let's go into those rules in detail and see how those rules, how you apply those rules and where to be worried about that. So, number 1, let's agree that we're all going to draw correct Lewis structures. And that may sound simple. Sorry about the small size on this, but let's go ahead and take a look at a typical example. Some of the textbooks that you see, especially the sophomore organic chemistry textbooks, love to use typesetting, like text messaging to draw the structures of organic molecules. And sometimes it's not so obvious what the Lewis structure should be. I expect you to be able to convert these kinds of representations over here when it's drawn out in this text form into valid Lewis structures like this acetamide molecule over here on the right. So that may sound easy, but when you first look at this, it looks like there ought to be an oxygen-nitrogen bond in there. So if you start to draw structures that look like this, CH3CONH2, well, that's not a correct Lewis structure. There's some atom in there that's not going to be obeying the octet rule. So critical that you obey the octet rule when you draw out Lewis structures. But remember, the octet rule is only for second row atoms: carbon, nitrogen, oxygen. What about fluorine? Yeah, but you don't see that much fluorine. What about boron? Yeah, but you don't see that much boron. Right? How hard could this be? Most of what you're going to see is carbon, oxygen, and nitrogen. How many electrons on hydrogen? Not 8. That's a different row of the periodic table. That's 2 electrons for hydrogen. So really, most of what you do in this class is just paying attention to the octet rule for carbon, nitrogen, and oxygen. Now remember, there are atoms, as once you drop down in the periodic table, for example, the sulfur, the octet rule doesn't apply to sulfur. So you've drawn structures for sulfuric acid or other types of molecules, phosphoric acid, DNA, phosphodiester bonds, and you can have more than 4 bonds to sulfur, more than 4 bonds to phosphorus. Those aren't second row atoms. Those will have a different set of rules. But most of what we do is carbon, nitrogen, and oxygen. Don't ever have more than 8 electrons on there. And if you have less than 8, it's not happy. Now, you'll see situations like this. Here's a picture of an N oxide. And with every fiber of my being, I want to make that minus charge attack the plus charge. Didn't I just say that Coulomb's law is so easy and obvious that we don't really need to go into detail there? This is an incredibly frustrated structure, but I want to encourage you, do not take the lone pairs on this oxygen and try to attack that nitrogen, because if you do that, you're violating the octet rule and then giving the nitrogen 10 electrons. You can't possibly draw this alternative resonance structure because you'd violate the octet rule. So this thing is stuck as N plus and O minus, and I guarantee you that wants to react to get rid of, right? The first thing you should do with your arrow pushing is use the lone pairs on the oxygen to get rid of that negative charge when you see an N oxide. If you understand the octet rule, then you're going to see structures that look like this and say, oh, that's okay. Nothing wrong with that. Right? If I draw 5 bonds to carbon and I don't have that positive charge there, that's completely wrong. But with that positive charge on carbon, there's no issue with that. So if somebody told you you can't have 5 bonds to carbon, I don't think they understood really the octet rule. We'll go into more detail about that to understand that. Okay, so when you draw out correct Lewis structures, you really need to put the charges there. So you might see representations like this. This group is called an isonitrile. You've never seen that functional group before. These are super smelly compounds, notoriously stinky. If you draw out the Lewis structure and you draw out the correct charges, you'll realize that there's a positive charge on that nitrogen and there's a negative charge on the carbon. And as soon as you draw those structures out, you kind of have an idea what to do, right? So you kind of have this idea, I hope, that maybe I ought to start my arrow pushing with the carbon lone pair. There's a negative charge on that carbon. That ought to be a smart way. And if you don't draw the charges, you might be mystified as to what should happen there. So practicing drawing correct Lewis structures is essential. We'll give you some practice in discussion sections starting this week and starting today. And again, draw the lone pairs. You know, I drew, when I took sophomore organic chemistry, I was such an anal loser. I drew every lone pair on every atom that had lone pairs. Every single one, even though you can't use more than one lone pair at a time. But you know what? It helped me to do well in the class. Maybe the practice of drawing all these lone pairs was helpful, because 95% of the time to 99%, let me just say 99% of the time, your first arrow will start with a lone pair. And if you've drawn them, you probably have a good idea where to start. So draw the lone pairs. It will help you. Okay, correct Lewis structures. You know, if we want to do arrow pushing, we have to draw correct Lewis structures. But I want to explain to you two types of bonds that we can't use for curved arrows. So one type of bond that you will see, especially if you take a class in biochemistry or chemical biology, is a hydrogen bond. And we usually designate those with dashed lines. There is clearly an interaction there. It means the hydrogen atom is vibrating back and forth between those two oxygens at about 10 to the 12th vibrations per second. There's something there, and you're fine to draw those. Just don't use that bond for arrow pushing. Once you start to use this bond for arrow pushing, nothing you do is going to be correct, because if I take electrons from that H, then in order to draw a correct product for that, I'm going to have to put a negative charge on that oxygen. And last time I checked, water doesn't have a negative charge on oxygen. You'd also end up with a positive charge on this other structure that's just, right? If I'm taking electrons away from there and it was neutral before, it better be positive there. And there's nothing, neither of those is now correct. Don't use curved arrows for dashed bonds, right? You can have H bonds in your structure, just don't use those bonds for arrow pushing. And most of the time, we're just going to leave those out. There's another kind of bond that you're going to see, especially in organometallic and inorganic chemistry, and that's dative bonds. Dative bonds are these situations where people don't want to draw the charges. It's like this. These bonds right here, the two bonds to H, I can barely fit this in here. Dative bonds like this, right, they don't satisfy, they are not valid Lewis structures. Right, if I've got two bonds to H and there's no charge on there, something's wrong. That's not a correct Lewis structure. If you try to use these bonds for any kind of arrow pushing, a dative bond, and there's clearly bonding there. When you buy borane from a supplier, it comes as this dimer. That's the way it looks. But we can't use this dative representation for arrow pushing. Whoops, I've got that arrow going to boron. That's insane. Well, actually, there's nothing sane I can do here with these arrows. I mean, if I break it here and take the electrons away from H, then I'm going to have a negative charge on boron. Or nothing I do there is going to give me correct charges. The product will have incorrect charges. Let me try to just break these bonds one at a time. So we're going to be messed up here. So dative bonds are great if you want to avoid having -7 charges on your transition metals. But when you try to apply them to arrow pushing, it's just going to be messed up. So here I would end up with a incorrect negative charge on boron and an incorrect positive charge on that hydrogen, and that's not right. So you could have a dative bond somewhere else in your structure, way away from the arrow pushing. Just don't use those dative bonds for arrow pushing. If you want to do arrow pushing, you have to draw structures that have correct charges on them. So in other words, I would want to come over here and I would want to change this structure somehow to be something that had correct charges on it. So let me give you an example. So if I'm going to draw this out and I want to do arrow pushing, I would have to change this around somehow to have a negative charge on boron. That's supposed to be a negative. Sorry, it's not well drawn. Some sort of a positive charge over here. If I wanted to do correct arrow pushing, I would have to draw a correct Lewis structure that had the correct charges on the structure. Sometimes I circle my charges if I think people can't see my handwriting well. Sometimes I don't circle the charges. There's no rule about that. It's just if you want people to see what you're doing there. So we have to draw correct charges if you want to do arrow pushing. Now you could use those bonds for arrow pushing because those charges fit the Lewis formalism. All right, our first rule was draw correct Lewis structures, and it sounds easy, but it's not that easy, so you need to practice that. And you should have had lots of practice drawing correct Lewis structures when you took an organic chemistry class. And like I said, we'll practice that when we get to discussion section, drawing correct Lewis structures. Okay, your second rule is all arrows should start with lone pairs or bonds. That sounds pretty simple. All arrows should start with lone pairs or bonds. Let's go ahead and take a look at this. You know, and I think lots of you have seen reactions of hydroxide. What is hydroxide going to do with acetaldehyde? Well, we know that hydroxide is going to attack acetaldehyde. Right? This is kind of the way you start. Most carbonyl chemistry is some sort of a nucleophile will attack the carbonyl. I think you know that alkenes get protonated by acids. So when you do hydration of alkenes or add HCl to alkenes, you know, when we draw these structures, this is incredibly wrong, the way I represented this. What you need to do is you want to make sure, let me switch to a black pen that is high contrast here for the, what you want to make sure is you avoid that mistake that I just showed you. Remember, there was a lone pair and I didn't use that. We'll come back to that in just a second. If I want to do the correct arrow pushing for that, whoops, I want to make sure that I start here with the lone pairs. That's what I said you needed to do. Start with the lone pairs. All arrows start with lone pairs or bonds. See my first arrow over here? This arrow right there started with a lone pair. This arrow over here started with a bond. Make sure your arrows start with lone pairs or bonds. Over here I want to protonate the alkene. I'm going to use the alkene electrons. Notice how carefully I made my arrow start in the middle of this pi bond. Right? I was super careful about this to make sure that arrow started right in the middle of the pi bond. Not on the left atom, not on the right atom, but with the electrons in the pi bond. That's what's attacking the proton. Now I understand that the proton just ends up on one of those atoms. But the goal of arrow pushing is to show that the electrons in that pi orbital are attacking the proton. Let me finish up that arrow pushing, make sure my arrows, I got to break a bond to that H. I don't want to end up with two bonds. So I'll start right in the middle of that sigma bond and then give the electrons to that O+, that oxonium ion. Okay, here's a substrate or a carbocation that really is ready to do a 1-2 shift. And so I can make the arrow start in the middle of this CC bond. There's electrons in there that are overlapping with that empty p orbital. That migration is fast. You know, the rate constant's about, the half-life for that's about a microsecond. Methyls are moving back and forth, shifting over and over. That's a super facile process. And so that my arrow there is very carefully starting from the middle of that sigma bond. So when arrows start from bonds, they should start from the middle of the bond, dead center middle of the bond. You don't have to touch the bond. That just makes it a little harder to see. But don't start from the one end of the bond or the other. Of a pi bond, double bond, triple bond, single bond, doesn't matter. Start from the middle of the bond. So I said all arrows start with lone pairs or bonds, and probably when you learned organic chemistry in your introductory class, you learned to think of things in terms of plus and minus, right? Why does chloride attack a carbocation? Well, it must be those charges there, right? That's why they attack each other. Why does hydroxide add to a carbonyl group? Well, it must be because of that negative charge, and carbon has a partial positive charge in the carbonyl. And if you learned it that way, it's going to mess you up. That's wrong. That's not why you attack a carbocation. You attack a carbocation because it doesn't have an octet. It's not the charge. Borane reacts at the same rate, and it has no charge on boron. And if you start using charges to attack charges, you're going to end up in this situation where you're doing things like this, where you see borohydride and you see an oxonium, some sort of an oxonium ion. I guarantee you, if you take that minus charge on boron and attack the plus, you're going to end up with something that does not make any sense. You'll end up with 5 bonds to boron and 4 bonds to oxygen, and it just will. Do not use charges for arrow pushing. You'll end up with things that don't make any sense, and you won't understand organic chemistry, right? We use arrow pushing to represent the interaction of filled orbitals with unfilled orbitals. Also, don't use arrow pushing to show the motion of atoms, and that will be confusing to you. So for example, I might say vocally, oh yeah, that bromine pops off. The bromine dissociates and goes somewhere. That's what I'll say. But that's not what your arrow pushing should represent, right? Your arrow pushing should not look like this, right? Your arrow pushing should not be used to show that bromine pops off. That's not what arrow pushing is for. Your arrow pushing should show, well, let me just put an X through that because that's killing me, right? Your arrow pushing should look like this. You break the bond and you give the electrons to bromine. You're not supposed to show the motion of the bromine atom. Or if I tell you to add a proton to carbon-2, protonate carbon-2, I'm telling you to add an H to carbon-2, but that doesn't mean your arrow pushing should look like this. That doesn't mean your arrow pushing should look like what I said. Your arrow pushing should start, right? It's the double bond that is the base and the nucleophile here. So don't do it like that. Start your electrons from the double bond and then attack the proton and break the bond. So you might have a tendency to make a mistake and listen to what we're saying and try to use arrow pushing to represent the motion of atoms. That's not what arrow pushing is for. I told you we're all going to agree. Well, I mean, if you don't have to agree, but I'm going to be the one grading the exams. We're using arrow pushing the way that Ian Fleming said would work well for us when we're trying to tell which things are fast and which things are slow. Okay, arrows are supposed to end on atoms or bonds. That's pretty simple. Make sure every arrow ends on an atom or on a bond. So let's go ahead and see how this would work, right? If I use water as some sort of a base and I protonate that with HCl, I would make sure my arrow ends on an atom. It's ending on the H atom. When I break this HCl bond, the sigma bond, I'll make the arrow end on chlorine. I think all of you have been doing this. You kind of know that arrow pushing, right? If I attack a carbocation, notice how clever I was? Boy, I'm so smart. I put that positive charge way on the other side of the molecule so I don't attack that positive charge. Don't attack the charge. Arrows are supposed to end on atoms, not on charge. There we go. That's going to form a bond to the carbon atom. Charges don't form bonds. Electrons form bonds. So we want our arrows to start with electrons. That's either bonds or lone pairs. And we want our arrows to end, unfortunately, on unfilled orbitals. And we don't have a way to draw unfilled, we do have a way. We don't typically draw unfilled orbitals like sigma star orbitals or pi star orbitals. They look complex. So that's why we have these rules. When we make an arrow end on an atom or a bond, we're trying to represent some sort of an unfilled orbital. Let's take a look at another example here. Let's go ahead and start. If we follow these rules, here's the end of an E1 or of an E1 elimination reaction. This is actually an uncommon combination, but right? If we want to pull this proton off and make an alkene, I would start with a lone pair, and I make my arrow end on the atom. And then I would break this HC bond, and I would make my arrow end on the atom. Right? So sometimes we draw the p orbital, but most of the time we'll just draw a plus. Don't make the arrow end on the plus charge. That's not what, it's not, even though it might look obvious. Now, I will allow you in this class to make your arrows end on bonds, even though that is not representative of the molecular orbital. And so I would allow you to do this, attack the atom, and then take the electrons in this HC bond and end in the middle of this pi bond. Your textbooks probably did a lot of this. That's why I'll allow it, but it's not as preferred as attacking the atom. So perfectly fine if you do this, because I think most of you will be used to showing yourself that I'm forming a pi bond when I break that bond. Now here's what they don't ever do. They don't ever just pop apart and go into nowhere, right? Again, you want to show that the bromine dissociates, but what you want to do is break the carbon-bromine bond and give the electrons to bromine. Make the arrow end on the bromine atom, not off in outer space. There's no empty orbital out there in outer space that you can add to. That's not what arrow pushing is for. So don't let your arrows end nowhere. They should end on atoms and end on bonds. All right. I'm going to give you something called the 3-arrow rule. And you might think, why do I need a rule that tells me how many arrows? That sounds so restrictive to me. So here's an example of maybe somebody did a deuterium labeling experiment where they wanted to see what happens if you take deuteroxide, hydroxide ion with a deuterium, and you hydrolyze an ester with that. I hope most of you could write out the mechanism for this transformation. I don't know if that's still something you remember how to do from your organic chemistry class, but hydroxide wants to attack carbonyl groups like this. And you can see the products here for this reaction. You're going to attack and break the methoxide bond, and then that deuterium is going to get picked up by the methoxide ion. So what's happening here is that you attack the carbonyl, you break the carbonyl, but then these electrons are going to be, when that carbonyl pushes back down the lone pair, you're going to kick off a methoxide, and then the lone pairs on the methoxide are going to grab the deuterium. Well, hold on, champ. You know, nothing about this looks right once we add all these arrows on there. This is a three-step mechanism. You can't put all the arrows for all three steps in one picture. Nobody will know which was supposed to come first. And you don't get a picture of those intermediates that might have diverted off and gone to do a different side reaction. We have to show the steps. So we have a 3-arrow rules that says don't draw more than 3 curved arrows in any step. It's just a safety device to prevent you from going haywire like this, because sometimes you get kind of excited. I do. It's like, oh my God, I can see it now. Let me put all the arrows there. So no, just put the arrows for one step and draw out the next step. It's not that hard to draw out the structures, the intermediate structures. So we have this 3-arrow rule that says don't draw more than 3 curved or curly arrows in a single step. So eventually you're going to get to the stage where you're an expert at arrow pushing. And then once you're an expert, if you think that those intermediate steps are so totally obvious, then I would encourage you to do something like this. You're not an expert yet, but when you are, you can do this. Draw the arrows for the first step, and then you'll generate this tetrahedral intermediate. And so if I think the next steps are obvious, then what I'm going to do here is I'm just going to draw 2 more arrows, right? And I'm not going to draw the arrow pushing for those arrows. If they're that obvious, I don't need to draw what's going on in steps 2 and 3, if it's that obvious. And if it's not obvious, then you should draw those steps out. So when you get to the stage when things are totally obvious and you think that everybody in the room sees what you're doing, you could stack the arrows like this. But you notice how this does not violate the 3-arrow rule. We are being completely consistent, and we're showing people what happens in that first step. Now, there will be cases, once you get beyond this course, well, even within this course, where a valid mechanism would have 3 arrows. So this is parole. It's a extremely reactive aromatic ring. And so it does electrophilic aromatic substitution and Friedel-Crafts acylation very easily. And the reason why it is so reactive in Friedel-Crafts acylation reactions is because these lone pairs on nitrogen are donating in to this pi system. And it makes not the nitrogen is not the reactive part. It's the CC bonds that are reactive. And so when you attack parole, you attack over here on this carbon atom. You attack over here on this carbon atom that is next to the nitrogen. And that's where you form a bond. Now notice I put 4 arrows there. There's no way I could have explained the reactivity of parole by using, well, I can. I'll show you how you could do it. Right? It's completely valid for you to use 4 arrows once you get out of this class. And there are cases like this where that's entirely appropriate. But let me remind you, there's always a way to obey the 3-arrow rule. You know, the reason why parole reacts the way it does is because there's a resonance structure. There's resonance interactions that look like this. And so let's go ahead and draw out that resonance structure. The resonance structure would look like this. And once I draw out this resonance structure, it is totally obvious to me why parole reacts the way it does. Right? There's a resonance structure that looks like this. And now I can see why parole reacts on the carbon next to nitrogen. And notice there's only 3 arrows in that first step. And when I draw this next step out, there's only going to be 3 arrows or fewer than 3 arrows in my next step. So when I draw that acylium ion there, sorry, let me try to switch to high contrast black. When I draw my acylium ion like this, now I'll have just 2 arrows. So I could have broken this up into 2 the first one isn't a step, it's a resonance structure. You can use resonance structures in order to stay within the bounds of 3 arrows. And oftentimes those resonance structures will be really helpful in teaching you the reactivity of organic molecules. So if you don't like drawing structures, this is really not the class for you, because sometimes you have to draw quite a few steps. but you learn about organic chemistry by drawing out these intermediates. Rule number 5, no termolecular reaction steps. What does termolecular mean? Termolecular means 3 molecules are involved. So here's an example of the start of, well, it's just an epoxide ring opening that's done in ethanol. And so you can kind of see what's happening here when you look at the product. When you look at the product, you're forming a bond between the O and the H, and you're forming a bond between the sulfur and the carbon. And that makes sense because we have a sulfur-carbon nucleophile here. And then it breaks open this carbon-oxygen bond. That's a strained bond with 27 kcals per mole of strain energy. And so that'll easily pull. Whoa, 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 whoa. You know, it looks right. It follows all the rules that I just gave you. But in order for this to happen the way I just said it would happen, it would require all 3 molecules to simultaneously collide with each other with just the right energy and just the right orientation. You know, when I take a mole of molecule A and I mix it with a mole of molecule B, they will be colliding with each other. And most of the collisions of any 2 molecules are not productive. Molecules just ricochet off each other, they bounce off of each other, they don't have enough energy, they don't have the right orientation. Only a very rare 1 out of 10 to the 12th collisions will result in a successful reaction. And if reactions are faster, more frequently. The chance that 3 molecules will simultaneously collide with just the right energy, and no chance. No chance. Do not draw elementary reaction steps where 3 things collide. Do it one at a time. Right? The way that this would happen is that the thiophenoxide, sorry, I'm having a little bit of a, not used to writing so small on my iPad here. The way you would draw this correctly is that you would draw this initially attacking. That thiolate anion is a great nucleophile. So first, collide the thiolate anion with that epoxide and break the bond in an SN2 reaction. And then in the next step, you can pull a proton off of ethanol. But don't have all 3 of those collide at the same time. It's not reasonable. It's not possible. It's not reasonable. It's a simple rule. But again, you might be, you know, it's just statistically impossible. And I think you'll, when you cover stat mech or something, if you take the physical chemistry series, they'll talk more about frequency of collisions and things like that, collision theory. I got one last thing we can get to. We won't get to the very last of the 6 rules, but I can get to this. You know, here's a reaction that all of you, I would hope, would vaguely remember, if not totally remember, and that's a Fischer esterification, where we use acid to catalyze exchange of groups attached to carbonyls. Exchange of esters for hydroxy groups, exchange for hydroxy groups with ester alkyl groups, alkoxy groups. And the role of the hydrochloric acid in there, it's an acid, and the role of that acid is to protonate the carbonyl. That's why you add hydrochloric acid in there. If you don't protonate the carbonyl, oxygen nucleophiles aren't going to add to carbonyls at reasonable rates. If you want oxygen nucleophiles, water, ethanol, some sort of a carboxylic acid, to add to a carbonyl, you've got to protonate the carbonyl. Now, when I draw this out, I've immediately made a mistake. There is no way for me to know that that's what happens. I dumped hydrochloric acid in there because we have to protonate the carbonyl. But let's talk about really what's going on in this reaction mixture. So initially, as soon as the instant that I mix HCl with ethanol, and ethanol is the solvent, that's the majority of the molecules in my reaction mixture, there's a fast and reversible acid-base reaction that occurs. Hydrochloric acid is the acid, and it's got a pK, you might not know this, somewhere on the order of about -8, -7, somewhere in that range. I don't know if you guys know the pKa for this oxonium ion over here, that I shouldn't draw that, I'm covering that up. That's got a pK somewhere on the order of -3. And we haven't talked about pKa's yet. And it doesn't even matter if you got these pKa's exactly right. The point is, one of these is a more powerful acid than the other. Hydrochloric acid is more powerful. Lower pKa's mean more powerful acid. And how much more powerful is HCl than that protonated alcohol? if you look at the pKa's, how much more powerful in factors of 10 is HCl? So pK is a logarithmic scale, and so how much more powerful of an acid is hydrochloric acid? It's 10 to the 5th. So that means that this side of the equation is favored. By how much? By 10 to the 5th. By 100,000 to 1. You will instantly reach an equilibrium where there's a 100,000 to 1 ratio of HCl and that protonated alcohol. The second you put the HCl in there, and you can't stop that from occurring. So which of these is protonating the carbonyl? What's protonating the carbonyl here? Is it this? Well, there's more of it. Or is it this? Well, it's 10 to the 5th more powerful. Is it the acid that's 10 to the 5th more powerful, or is it the acid that's 10 to the 5th more abundant? This is 10 to the 5th more powerful. This is 10 to the 5th more abundant. You have no way to know that. I have no way to know that. So if I draw out that it is HCl that's protonating that carbonyl group, then I'm overstating what I know. There's no way you could know what's protonating. And in fact, in solution, it's probably both of them protonating the carbonyl. So when we come back, I got to end the lecture here. What we're going to do is introduce this idea of using symbolic acids like HA and A-. If you need an acid, use the symbol HA. If you need a base, a conjugate base under those conditions, use A-. And then we don't have to worry about is it HCl that's protonating it or H3O plus. You don't even know the right answer to that. Nobody knows. So we're going to encourage you to use symbolic HA and A- as acids and bases, or if the conditions are basic, BH and B plus, BH and B. So, okay, we'll continue on from there. Go to discussion section. Yeah, question. Yes, there is discussion section this week. So if you're in the Monday discussion section, we'll see you at 1 o'clock. And we'll talk about Lewis structures and just simple arrow pushing. All right, just before we left on Monday, I described this situation where you're going to see proton transfers occurring in your mechanisms. And you'll be tempted to draw things like this. But you won't really know what is transferring the proton to that carbonyl in this reaction. Right? Is it the acid that's present that's 10 to the 8th more powerful? Or is it the acidic species that's 10 to the 8th more abundant? You're never going to know. You can't know what is transferring the proton. And it could be other protonated carbonyls that are added, transferring from one proton from one carbonyl to the other. So we have to have a way to avoid saying things that we don't know and worrying about what's actually serving as the acid in these types of arrow pushing events. And so in this class, what we're going to do is we're going to tell you that what you need to do is when you're doing proton transfers in mechanisms, in intermediate steps in the mechanism, and you're in that situation where nobody can know what's doing the proton transfer, what you should do is follow this two-step guide. Step 1 is to decide if the reaction conditions are acidic or basic. That's what you need to decide. Right? If you see somebody adding an acid catalyst to a reaction like hydrochloric acid or sulfuric acid, the conditions are acidic. If you see a reaction that generates HCl as a byproduct, well, by the end of the reaction, there's going to be a full equivalent of hydrochloric acid in there. The conditions are acidic. If you see somebody adding a base, like triethylamine or potassium hydroxide, the conditions are probably going to stay basic. And what happens if you absolutely can't tell? If it's done in neutral water and it seems like it, well, you use either one, HA or B as your symbol. So if the conditions are acidic, you should use this symbol for your acid. HA is going to be the symbol that you'll use for acidic conditions. That will be your acid, and you don't have to worry about whether it's H3O plus or HCl or a protonated carbonyl. Just use the symbol HA and don't worry about what is the identity of A. And if you need a base under those conditions, use the conjugate base A minus. Just draw a lone pair on that A minus and use it to pull protons off. There, you've got an acid, you've got a base, and that's what you should use if the conditions are acidic. So here would be an example. Let's suppose that under acid-catalyzed conditions, we're interested in this tautomerization of an enol into a keto form. And that's a two-step process. The first step in this mechanism is that we're going to put a proton. I hope you can see here that you're going to put a third proton on this carbon atom. And that turns out to be the first step under acidic conditions. So let's go ahead and draw out our symbolic acid here, HA. Again, we don't care what's transferring the proton. We just know we need to put a proton on this enol carbon. And let's go ahead and draw out the arrow pushing here. I've got lone pair here. I'll push down. That's why that alkene is so basic. That's why that alkene wants to be protonated. And the alkene wants to be protonated right here. There we go. We pick up a proton, and that makes our next intermediate. And so the next intermediate in this mechanism looks like this. And we've got this proton. I don't need to draw that proton. Now watch this. I'm very smart. I've done this mechanism so many times, I know to draw that HO bond because I need to break that bond in the next step. I can tell there's no proton on that carbonyl in the final product, so I'm going to have to remove that H. You have to draw a bond if you're going to break a bond. So now I come in with my A minus. I need a base under the conditions of the reaction. Here it is. I'm going to use A minus. I'll draw a lone pair on that. And so now when I come back over here, now I could just give the electrons to that oxonium ion. Oxonium, that's oxygen with 3 bonds as an oxonium. Okay, that's how to use HA and A minus when you need an acid and a base for proton transfers and you believe the conditions are acidic. Let's take a look at an example of a situation under basic conditions. Suppose you're transaminating an ester or something, and you need to transfer a proton from over here on this oxygen, and you need to get it over to this nitrogen. And this would be a great case if the conditions are basic. You've added amines to the reaction, and the conditions are basic, and so you need some sort of a base. So let's start off with B. I'll just go ahead and draw B, and I'll draw a lone pair on the B. If it's triethylamine, it's neutral, so I would draw B as neutral. Then we come over here and we draw the arrow pushing. Let's pick up the proton from the HO. And we'll draw that intermediate here. So now we've got O minus. Yep. Somebody, we've still got that ring there. Doesn't really matter that much. And look at this. In the process of pulling that proton off, we've generated the conjugate acid. Since B was neutral before, I'll put a plus there. If I decided to write B minus, I should try to keep track of charges and write neutral B. So now the BH is right there, and it's ready to stick the proton right back onto that nitrogen atom where we want it to be. There we go. 2 steps, proton transfer, right? Once you decide that your reaction conditions are acidic, stick with HA and A minus. If you decide the reaction conditions are basic, stick with B and HB. Don't mix up HA and B, right? That's not correct. You'll end up with weird imbalanced equations with too many symbols floating around. Now, I'm going to encourage you. You could see what I've done here over in this second type of a reaction. All I wanted to do was move a proton from one atom to another. And in both of these cases that I drew out for you over here, this top case and then in this bottom case, in theory, you might have tried to draw something that looked like this, just a one-step proton transfer. But I'll tell you right now, there are not plausible proton transfers that occur through 4-member transition states. Right? That's not going to be plausible in this class. You have to pull a proton off and put a proton back. 2 steps. Don't transfer protons through 4-member transition states. This is impossible. It violates the concept of orbital symmetry, the quantum mechanical concept of orbital symmetry. We may get to that later when we talk about paracyclic processes, why this 1-3 shift is not allowed by paracyclic selection rules. So again, we're going to be doing a lot of proton transfers in this class. It is the most common type of mechanistic step when you do arrow pushing mechanisms for polar reactions. Yeah.
In the acidic conditions reaction, in the first arrow, is it going towards the carbon or the sigma bond?
So you can see right here that as I push the electrons down, I'm going to create a CO double bond. So I can't add the proton to this because then I'd end up with 5 bonds to that carbon. Now, this is the frustrating thing about using bonds to attack. You notice how careful I was to draw my arrow starting from the middle of the bond? You have to start your arrow from the middle of the bond. You're not going to be able to know until I draw the product where I put the proton. And it's frustrating. Some people feel like, well, I've got to make my arrow show people where the proton's going to add. That's not what arrow pushing is for. Arrow pushing is to show you that the pi electrons centered in the middle of that bond are attacking the proton. And they will end up on the end carbon You can see it in the product that the proton had to end up on the end carbon because you end up with a CH3 group at the end. So if you look all the way to the product, you can tell where the H had to add. But that's going to be frustrating to you, that when you use bonds, single bonds, double bonds, triple bonds, to attack things, the arrow pushing doesn't show you which of the two bonded atoms is going to be forming the bond. And okay, let's go ahead and talk about our last rule for mechanistic arrow pushing, and it's a pretty simple rule. And the rule is that H is always attached to something. It is always attached to something. Nowhere in your reactions, nowhere in anything you write should there be an H that is not attached to things. So the challenge here is that in organic chemistry we use terms like, oh, proton, you add a proton to that. Hydride, oh, that's a hydride reduction. If we did radical chemistry, we'd be talking about hydrogen atom transfers, abstract a hydrogen atom, donate a hydrogen atom. But these are just terms. They refer to functional groups. They do not refer to free species floating around in solution. So if you draw something that looks like this is completely wrong. There's no such thing as H plus floating around in any organic reaction. Right? If you want to find H plus, just free protons, go to the center of the sun where there's nuclear chemistry and plasmas and stuff like that, and you'll find plenty of just protons floating around by themselves. But not in any organic reaction that you're going to be exposed to that occurs under normal solution phase conditions. If we do radical chemistry, we might talk about hydrogen atom addition. For radicals, we use slightly different types of arrows, but again, there's no such thing as just a hydrogen atom H dot floating around in any reactions. It's attached to something, right? And if we talk about a hydride reduction with lithium aluminum hydride or sodium borohydride, there's no species called a hydride anion that's floating around. Sodium hydride has a sodium and a hydrogen bond on it. In fact, it's got the sodiums and H's have multiple bonds to them, as long as they don't violate some like 2-electron or octet rule. So how do you, what would be the correct way to do this? It's not that hard to obey the principles that we've showed you. If you really wanted to stick a proton on this acetal right here, then draw HA. Show that it's attached to something from beginning to end. There you go. That's not that hard, and it's completely realistic, right? That's how you avoid writing H+. It is not that hard to write HA and break the HA bond. And in the process of doing that, you're going to generate A- that you will probably need in a later step in the mechanism. So don't write H+, don't write H-. Those species don't exist in organic reactions. It just doesn't make any sense. Okay, so the corollary to that is you need to avoid any step that's going to release an H+. So don't do anything that looks like this, right? That doesn't make any sense because then you're going to release this H+ species, and that's not right. So what you want to do in a case like this is kind of obvious. If you're under acidic conditions, you use A-. You would typically have these oxonium species in acidic conditions. So you use this conjugate base left over from your acid. That's what's going to pull off the proton here from this oxonium ion, from this protonated carbonyl. And so I would simply pull the proton off. That's the correct way to do that. And if you do that, you'll end up with a byproduct that's HA, ready to serve as an acid. I'll just put a little quote here to indicate the acetone is the same. So now you've got HA ready to do more acid catalysis in your reaction. So don't draw H+ ever in our class. Don't write H dot, don't write H-. Those things aren't realistic. You'll often see in books and in the older research literature, really, people write stuff like H+. Now, I know every single reagent on the shelves of our, and I'm pretty sure, and I've never seen a bottle of H+ in my career. Right? If you go to any research laboratory or chemistry laboratory or chemical supply house, there's no such thing as a reagent called H+. Right? If you were using sulfuric acid, then write sulfuric acid out. It's not hard. Or if you just wanted to be sophisticated about it and you didn't know what the acid catalyst was, then write quotes or write catalytic HA there. Or if you had to write catalytic H+, you could put quotes around either the cat H+, or put quotes around the H+ itself, just to show people that you know, okay, I realize there's no such thing here as H+, but if you put quotes around it, at least people know that you know that that's a complete fiction and is not realistic. So don't write H+ as a reagent, Write real reagents, catalytic HCl, catalytic sulfuric acid, catalytic pyridinium tosylate. Write real reagents instead of, because H doesn't just fly around as a free proton in normal solution phase chemistry. All right, those are our rules for mechanistic arrow pushing. We're practicing those rules this week in discussion section, just drawing out Lewis structures, drawing out simple mechanisms. Well, not all simple, but some of them relatively simple that you might have seen in a sophomore organic chemistry course. So rule number 1, remember, draw correct Lewis structures. That's the way we start. You have to, if your Lewis structures aren't correct when you start, you're not going to end up anywhere good by obeying arrow pushing rules. Make your arrows start with bonds or with lone pairs. And 95% of the time, more than 95% of the time, your first arrow will start with a lone pair. Your first, right? So make arrows start with bonds or lone pairs. Usually the first arrow starts with a lone pair. You make your arrows end on atoms, and then I'll accept it if it ends on a bond. But your arrows don't end in empty space, right? We're trying to somehow indicate that your arrows are ending on an unfilled orbital. I gave you this 3-arrow rule. Don't have more than 3 arrows in any step, in any mechanistic step. Right? You'll just end up with these. Nobody will be able to tell what was the first step if you try to put 8 steps and all the arrow pushing in one figure. Break it down, break every mechanism down into elementary reaction steps that consist of one transition state. So don't draw termolecular elementary steps where 3 things simultaneously collide. That doesn't happen. It's not realistic. It's hard to get 2 things to collide. It's like herding cats. You just can't get 3 molecules to simultaneously collide with the right energy and orientation. So today I gave you these extra rules. Use these symbolic acids and bases, HA and A-, under acidic conditions, or BH and B if you're under basic conditions. And just make sure that H is always attached to something when you draw out your mechanisms. Yep.
Could you go back to slide 18?
Uh,
Under the basic conditions, what is allowing that lone pair of the amine group to attack the hydrogen? My thought is that the oxygen species would be more reactive.
the O-? Yeah, so the question is, why doesn't this O- come back and pull off the proton? That's happening. I'm just trying to show how you go forward to the product, but that doesn't stop there from being reversible reactions. So oftentimes I'll suggest a plausible arrow pushing mechanism that tells people to go from here to here, or I guess in your direction, left to right. And that doesn't say there's not back reactions, and that doesn't say there's not other equilibria that are occurring. You're not obligated to show every single process that's occurring in the reaction. You're just obligated to show the steps that get you to the product, not every single thing that's occurring in the reaction mixture.
For that same problem, would it be possible if now that the oxygen has extra lone pairs, could that form a double bond and then causing the release of the nitrogen?
So the question that you're asking is this going to happen next? Absolutely. That's the next step. This is like the middle. I just took the middle 2 steps from a longer mechanism. Carbonyl bonds are stable. Formation of CO double bonds drives, 80% of organic chemistry. You burn stuff, you form CO2 with C2CO double bonds. CO double bonds drive, or formation of carbon-oxygen double bonds drives so much of polar organic chemistry.